This is further statistics one sample paper. Let's just do it. So this is clearly a Poisson distribution because you've got an amount per time or per something. I'm going to split this into 2.5 per half litre just because that's what the sample is doing as well. So x2 is Poisson with 2.5, lambda is 2.5. The null hypothesis will just be that lambda is 2.5, and the alternative hypothesis, we're testing whether it's greater. So we're going to be greater than 2.5. If we get out the Poisson table and look for 2.5, and we're looking for a value that's bigger than 0.95, aren't we? So the first one we see is this one here. So the probability of x being less than or equal to 5 is this, which means the probability of x being greater than or equal to 6 is 1 minus this, which is that. And that's within the critical region, it's less than 0.05. So we'll reject anything that's 6 and above, and our sample was 7. So therefore, we will reject the null hypothesis. There is evidence that the number has actually increased. And that's the first question done. Good. Question number 2 then is about binomial this time because you've got a probability P. And now in every 5 calls, the probability of at least 1 being wrong is this. So the probability of x being less than or equal, sorry, being greater than or equal to 1, because that's at least 1, isn't it, is this, which means 1 minus that means the probability of x being less than 1 is that, just doing 1 minus this. But the probability of x being less than 1 in a binomial, because you can just take integers, is just the probability of x being 0. So we just get this. And now the probability of x being 0 is, what that's saying is that every call was correct. Now the probability of a call being wrong is that. So the probability of being correct is 1 minus p. And for all 5 of them to be correct, that's going to be 1 minus p to the power 5. We just need every single one to be correct. Of course, we take the fifth root, which is pretty much this. You do 1 minus and you get this. So now we can say x is just a binomial distribution with 1,000 calls, probability 0.01. This was just a very complicated way of them trying to get you to work out what the probability was. Now that we've got it, we're good to go. So the mean is just NP. So that's just this times this. That's the mean. And the variance is NP 1 minus P. So this is NP, this is 1 minus P, and we'll get that there. And we'll have that done there. Using a Poisson approximation, now Poisson approximation uses this as the lambda, just the mean, so we're just going to use that as the mean there, as our lambda, sorry. More than 6, so we're looking for the probability of more than 6, which is the same as 1 minus the probability of less than or equal to 6, and we can just use that in a calculator, right? Just find probability Poisson CD and type in lambda as 10, and you're looking for x to be 6, and the calculator will give you this. Explain why this is valid. You can't just say that n is large and p is small. You need the context. You need to say the number of calls is large and the probability of calling the wrong agent is small. So get the context in there. The Mark's team was quite specific about that. The probability that more than 6 are connected wrong using the binomial is this. Comment on my accuracy. Again, just mathematical speak here. The approximation is accurate to within 2 decimal places, and that's all you have to say. Question number 3 then. So we've got this thing about, it's the chi-squared test question. So firstly, we need to work out these 2 things here. Now we can use a binomial for that, of course. So he's saying this is the binomial here, probability this and this. So for 2 of them to be wrong, that's going to be you can just put it in the calculator, right? You could just say binomial distribution, binomial PD, because you're just looking for exactly 2. You type in this, you type in that, you get that number out. Now, of course, we need to times that by the sample size of 150, and we'll get that, which is our number here. And likewise, for 4 or more, you could do probability of x greater than or equal to 4, or you could just notice that you just want to do 150, take away all of these to find this, because these need to add up to 150, and we end up with that. Now, when we're doing our chi-squared test, there's a few things we need here. Firstly, you need to state the h0 and the h1, which you just say the binomial is either suitable or not suitable. That's just what you do every time. And now the chi-squared test doesn't work if if one of these is less than 5. So let's group up these 2 things here, add this and this, add this and this, and just say 3 or more is this. And now we're good to go. The degrees of freedom are 1, 2, 3, 4, minus the fact that these just has to add up to 150. So that's the 1 restriction. So 4 minus 1 is 3. You look up in the chi-squared table for V. This isn't really called V, but I call it V anyway. 3. And then, of course, we're looking for 5% significance, which is going to be this bad boy over here, and we end up with that figure there. So that's going to be our first thing there. And then, of course, we follow the formula. Now, I prefer using this formula. If you don't, then that's fine. It's up to you. But this is just our observed frequency. So it's this squared over our expected is this. And then we just do all 4 of those added together. So this squared over this, this squared over this, this squared over this, and so on, added together, and then take away n, which is 150, and we end up with that. Now that's greater than this, so we're within the critical region, and so we reject h naught, and that hopefully is all 10 marks there. Cool. Now we're on to the next question. So the assistant manager thinks that binomial distribution is a good model, but it's just the proportion of fake coins is higher than this. So she calculates the actual amount proportion of fake coins in the sample, and then extrapolates that to find these expected frequencies, is what she's doing. So yeah, and her expected frequencies are shown in here. So explain why there are 2 degrees of freedom. Now, firstly, we have to collapse these 2 rows. So that removes, that makes 4 columns. This is less than 5, so that will make 1, 2, 3, 4 columns. And now to get down to 2 degrees of freedom, we're going to do 4 minus 2. So where do the 2 restrictions come from? Well, one of them is that these need to add up to 150. And the other one is that these need to be in the proportions that she's calculated from the sample. Because it said she calculated from the actual proportions. So that's the 2 restrictions. They must be total up to 150, and they must meet the proportions that she's calculated from this original sample that was made. So okay, we've got those 2 things, and then of course 4 minus the 2 restrictions give you 2 degrees of freedom. So we're going to use the chi squared thing. Now I typed this in. I just did this squared over this plus this squared over this. But of course that just gives you the thing that they told you to get. I wasn't really concentrating and wasn't looking at the number of marks. I just did this and then noticed that they've already told me the answer to that. So that's fine. And now test the thing. Use a 5% significance. So you get out the chi-squared table. So I mean, write h1 and h0 as always. Get out the chi-squared table, and now we're looking for degrees of freedom 2. So we're looking for the second one, and again 5%. So we're looking over here, and that's this number here. So anything more than that, and we would reject. But we're actually much less than that. So we're not in the critical region, not even close. So we're going to reject the fact that this is a bad model, and we're going to say the binomial distribution is probably quite a good model for this, and that'll be that done. 4 then, so Poisson distribution mean this, a sample of this. So this is central limit theorem, whereby the idea is when you take a sample from any distribution, that sample is normally distributed. So we're going to say this, and this is the formula that you use. So we've got x bar is twiddles n, with this as the mean, and then it's going to be sigma squared over 100, but of course sigma and the mean in a Poisson, sigma and the mean are equal to each other. So we're just going to say that, sorry, not sigma and the mean, but mean and variance are equal to each other. So therefore, we could, this is variance, isn't it, sigma squared. So we're just going to put in 2.3 for this and then divide by 100 because that's what this tells us to do. Now, at this point, all we have to do is say we're looking for the probability to be greater than 2.5, which is the same as 1 minus the probability of being less than. And now we can just use our calculators with the normal distribution with, this is all the things I typed in, normal CD, variance, lower, I just put in a massive negative number, upper this, and then mean is this, and standard deviation, of course, is root of all of this. And if you type that in, you get this thing here, 1 minus that is that thing there, and we should be good to go. I got really annoyed because the mark scheme actually has those 2 numbers flipped over, and I did this in a couple of different ways, and I kept getting 3.6, not 6.3, and I concluded that the mark scheme is incorrect. But if you definitely think I'm wrong, then tell me about it. So the probability of Richard winning a prize in game is this. He plays a number of games. Find the probability he wins the second prize on the 8th game. Now, what that requires, I'll use this table in a second, is for him to win 1 prize in his first 7 games, and then definitely win the prize on his 8th. So the probability of winning 1 prize in his first 7 games is 7 choose 1, because you want to know, you want 1 game where he wins 1. This is the probability of winning 1 game, and then this is the probability of losing with 6 games. So it's a binomial, of course, and we want to win 1 and lose 6, and we can win any one of those 7. And then we need to times that by the probability of definitely winning his 8th game, which is just times 0.15. And we get that, and we get this number here. State 2 assumptions we made. So we've assumed that all of the things are independent, the results are independent. We have to assume that for a binomial to work. And we've also assumed that he doesn't get better at the game as he plays it, and that this p-value is going to stay the same all the time. Next, Mary is playing the game, but has a different probability of winning. She plays until she's won R prizes. Now, that's a negative binomial distribution. So, okay, let's keep that in mind. Variable G represents the number that she's won. The mean and standard deviation are 18 and 6. Now, it's a negative binomial, and mean is given by this, so we'll put that in, and variance is given by that. Now, variance is standard deviation squared, right? So this is going to equal 6 squared, or you can write the square root of this is equal to 6, and then square both sides. Of course, we can rearrange that for R, then we can put that in there, and we can solve this by doing a bit of expansion and a bit of rearranging, and we'll get P as this. This is bigger than 0.15, and so therefore Mary has a better chance of winning the game. Okay, question 6 is the probability generating function question. Show this. So a key fact of the probability generating function is gx of 1 is equal to 1 every single time. So we're just going to put 1 in here and solve for k. Very quickly we get this. That's fine. Find the probability of this. So what we need to do here is you can expand all this out and you get this. So just imagine another copy of this here and do 3 times 3 and then 3 times t, and then another copy of t times 3 is 6t. And then, of course, 3 times 2t squared plus another 2t squared times 3 is 12t squared. And then keep going, keep expanding, you get this. And now the probability of x being 3, you're just looking for the coefficient of the one. I guess these two can actually go together, actually. But you're just looking for the coefficient of t cubed, which is going to be 4 over 36, which is a 9. So that's a nice little fact you can use there. Show the variance of this. This is actually in the formula book. If you look hard enough, the variance is given by this. So we need to differentiate the function a little bit. I've actually chosen to differentiate this one. So bring the 2 down, 2k into this to the power 1, and then the derivative of this is 1 plus 4t. And then I just differentiated that again. I actually used product rule just because I was being fancy. So 2k left alone, differentiate this for 1 plus 4t, leave that alone, and then leave that alone, differentiate this for 4. And then we can just put in 1s into these. Of course, k is 1 over 36, which I could have written in here, but anyway. So 60 over 36 is this, and then again, put in 1 into there, and then evaluate it. K is 1 over 36 as well, and you get this. And then you just shove those 3 results into here, and you get the variance as this, as we wanted to get. Super useful result in this last thing here. If you just set like y to equal this, the generating function of y, you take this number and raise it here in front, and then this number, and then that goes inside. There should be a second bracket closing this up, but whatever. So we times this function by t first, t to the power 1, just t, and then we also, every time we see a t, I think I actually use this function because it's easier. So times this function by t, which gives you t over 36 at the front, because k is 1 over 36. And every time we see a t, input a t squared instead. So t squared and t to the 4, and we'll end up with our answer there nice and quickly. So super useful result to remember here, which I would recommend you use. The last question then, so we've got testing a spinner to see if it's less than this. They both use 10% significance. Cool, so 20 times record the number of times allowed head. That sounds like a binomial to me. So we'll do this, critical region. So we just look up the binomial tables. N is 20, P is 0.2. We're looking for less than 0.1, which is going to be this one. So it's going to be P less than or equal to 1 is going to be our answer. So just less than 1, I guess. That should be less than 0.1, of course, 0.1. So therefore, the critical region is less than or equal to 1. Yeah, so that should be less than 0.1 was what I was looking for. Write down the size. The size is just the number you get when you do this. So it's just this here. Tessa decides to spin it until she lands on red. So that's a geometric one instead. Again, probability 0.2. Super useful result here. This doesn't work so well because that's equal to x. That's the likelihood of. So this here is the probability of getting x to be of like landing on exactly the 5th roll. But we don't really want that. We want to find the probability of landing on a greater than or equal to roll. So because we want to essentially find the x such that the probability of waiting that long until you get a red is less than 0.1 is what we're going to say. We're going to so we just want greater than or equal to. And this is a super useful result, again, that I would recommend that you just know because it's not in the formula book. And we're going to use it twice in the next 5 minutes. So we want the probability, we want for some number of spins, we want to wait that long such that the probability of that is less than 0.1 because that's the critical region. And of course, what we can do is we can substitute this idea into here with p is 0.2, which gives you 0.8 to that. You can take logs of both sides. Now be careful. When you take log of both sides here, log of 0.8 or log base 0.8, whatever, that flips the sign here because that's just what happens when you take logs. You could also think about taking, essentially, it's a bit like timesing by -1, and you just flip over the sign. If you forget to do that, it becomes quite obvious that you've made a mistake when you get an answer of x is less than this, and like that clearly can't be a critical region, x less than some number. So, or at least not in this case. So we're looking for x to be 12 or greater is our critical region. And again, our size of the test, well, we don't actually have that figured out yet. What we need to do is we need to put 12 into this function here. So into here, 0.8 to the power 12 minus 1, because that'll give us the actual number. So essentially what this is saying here, because of course that's less than 0.1, that's the answer, because if we put in 11 here, we'd get something slightly bigger than 0.1. So if you imagine if the geometric tables existed, which they don't for us, that would be the number we would have looked at, just like we did earlier. Show the power function of Sam's test is given by this. So the power of a test is the probability that you reject H0 when H0 is false, is the idea behind the power. So rejecting H0, or we reject H0 when x is less than or equal to 1. So it's the probability that x is less than or equal to 1, given H0 is false, means that x doesn't do this. X is a binomial with some other p-value here. Now, of course, we can just evaluate a binomial function because we know how binomial functions work. This is the probability that x is either 0 or 1. So here's the probability x is 0. When you have 20 choose 0 into 1 minus p, because we don't ever want p to happen. We want the other thing to happen. So 1 minus p to the power 20 plus, and then you want 1 p events to happen. So that's 20 choose 1, p times 1 minus p to the 19. You can, of course, 20 choose 0 is 1, 20 choose 1 is 20. You can factorize out at 1 minus p to the power 19, which leaves behind 1 minus p to the power 1, I guess I could have put here, which is just 1 minus p, plus these 20p's here, and you get what they wanted you to get. The power function for Tess's test, now that's just the probability, again, same idea as here, probability that x is greater than or equal to 12, given that you've got a geometric sequence that's, sorry, geometric distribution that where p isn't, the p that we thought it was, it's just some random p. But of course, we use the same result I did on the previous slide, right? This exact same result. So therefore, this is just 1 minus whatever p is to the power 12 minus 1, which is 1 minus p to the 11. And we have this. So super useful result. And we have that series as well. With reference to all of this stuff, give reasons whether you do this or this. So the size of Sam's test is smaller than the size of Tess's test. Now that's useful because the size of test is the chance of rejecting H0 when it's true. And that's not what you want. You don't want to reject a test when it's true. You don't want to reject the null hypothesis when the hypothesis is correct, right? So the fact that his test has a smaller chance of doing that is good. So that's points for Sam's test. Secondly, when we evaluate the power of the tests, now they've given us p as 0.15, so we're going to put that into here and put it into here, and we get Sam's test has a higher power. And now what that means is the power is the chance of rejecting H0 when it's not true, as we said in the previous slide. So the fact that Sam's test is got a larger chance of doing that, it's got a larger chance of rejecting H0 when it's not true, a larger chance of doing the correct thing, means that Sam's test is better, and therefore it's better on both fronts, right? And so it's definitely recommended for p is 0.15. Now, I slammed that in there because now this doesn't really depend on p, the size, but this does, right? This definitely does depend on p. In fact, I think this also depends on p, going back a little bit. But this depends on p, doesn't it? So there's a chance when p is different that Tess's test would be better, but for p is 0.15, Sam's is better for sure. Thank you for watching, and I'll see you next time.